In this video, I'd like to discuss the subject of unit vectors. Now, unit vectors are incredibly useful to us, especially when we're solving problems with vectors in computer graphics and programming. Now, the reason they're useful to us isn't going to really become apparent until later on in this DVD when we start applying unit vectors to solve problems. However, I wanted to introduce the idea of unit vectors, talk about what they are, and how we can convert a normal vector into a unit vector in this video. So what exactly is a unit vector? Well, a unit vector is any vector that has a length of 1 unit. So if we had a vector v, v would be a unit vector if and only if the length of v, so the magnitude of v, is equal to 1. So again, a unit vector is any vector that has a length of 1 unit. And there's a special notation, much like the way we're saying v is a vector with a small line above, or much like we're saying we're finding the length or the magnitude of v with the magnitude symbol. There's a special notation that says that a vector is a unit vector. And that's to draw the letter, the variable name, if you will, of our vector with a small hat symbol above it. So much like this means that v is a vector, the small line tells us that v is a vector. If you see a variable name with a small hat on, it means it is a unit vector. That's a special type of vector that has a length of 1 unit. So if you saw v hat, v is a unit vector. Likewise, if we had a hat, a is a unit vector. If we had b hat, b is a unit vector, and so on. And you may well encounter this in mathematical texts. You may well encounter in part of the problem that they're trying to solve, they may say, we have a vector a, and they'll write a with a small hat on. They won't explicitly say that a is a unit vector because they'll be expecting you to realize that by putting a small hat on top of that unit, or on top of that vector's variable name, that means it's a unit vector. So if you encounter a vector variable name that has a hat above it, that means it's a unit vector. It has a length of 1 unit. But why might we be interested in vectors that have a length of 1 unit? Well, to understand this, we need to think back to the whole concept of what vectors are. We recall that vectors contain 2 pieces of information. They contain a direction and they contain a magnitude, a size of value. So the size of the value is stored in terms of the length of the vector, the magnitude of the vector. So usually vectors have 2 pieces of information. They have a direction and they have a length. However, unit vectors, by having a length of 1, we can really think about these as encoding direction only. They're not really encoding length. I mean, they are encoding length. They have a length of 1. But when we start solving problems with them, we'll realize that this length, because it's 1, kind of cancels out any relation the length has to the problem and means that we're dealing solely with finding things that relate to the direction of the vector. And this can be very useful because there are a number of problems that we might be trying to solve where the length of the vector really isn't that important. It's just the direction of the vector that is of importance to us. And so unit vectors kind of, it's not mathematically rigorous, but they kind of encode direction only and not length. So they are incredibly useful for that reason, and because of the fact they have a length of 1, we'll see that calculations later on become a lot more simple, and that's useful for us in computer graphics because the more simple the calculations, the quicker they are to evaluate on the computer, and that means that anything we're doing using these unit vectors is going to be quicker than if we were using normal non-unit vectors. But what if we had a normal vector and we wish to convert it into a unit vector? Well, this is a process that's called normalizing. So allow me to scroll down. So this is called normalizing. So if we have a vector, and this vector could have any length, and we wish to convert it into a unit vector, we need to normalize that vector. Well, how are we going to go about doing that? Well, let's say we had a vector, and this vector had a length of 20 units. If we want to keep this vector with the same direction, but we wish for it to have a length of 1 unit, what we really need to do is shrink our vector down, scale it down, so that it's pointing in the same direction, but it has a length of 1. Well, we've seen how we can scale a vector. We've seen that if we multiply a vector by a scalar value, for example, a scalar times a vector v, we've seen that this effectively scales the length of our vector. It doesn't change the direction of our vector unless, of course, we had a negative scalar. But if we have a positive scalar, it doesn't change the direction of our vector. It simply scales the size of our vector. So in this case, where the length of our vector is 20, what we'd need to do is we'd need to scale it by a scale factor of 1 over 20. If we think about this, we'd be making it 1/20th of the original length. Well, 1/20th of the original length of 20 is going to be 1. So if we had a vector v that was equal to xy, and if the length of v was equal to 20, then what we'd want to do is we'd want to scale v by 1/20th. We'd want to shrink it down to 1/20th of the original length, because its original length is 20, and that would give us a length of 1. So this, if we were to sort of work this through in terms of the components, this would give us 1/20th times xy, which we know is going to give us a vector that has 1/20th of x and 1/20th of y. But we know this is just a number. So we have a number 1/20th of x. So we have this number 1/20th of x, and we know if we have a fraction and we multiply that by another value, we could equally write this as being x divided by 20. Hopefully that's quite obvious. If we're taking 1/20th of x, if we're multiplying x by 1 over 20, this is the same as taking x and dividing it by 20. The same can be said here. We've got 1/20th of y. So 1/20th of y. This is the same as taking y and dividing it by 20. But where did this 20 come from again? If you recall, this 20 is the original length of our vector. We said our vector has a length of 20, so we wish to scale it by 1/20th. So what we're really doing is we're saying we're taking our x and our y, and we're dividing x by the length of our vector, and we're dividing y by the length of our vector. So we're finding the length of our vector, and whatever that is, we're dividing both the x component and the y component by the length of our vector. And there's a way that we can write this. We can say that if we have a vector v, well then the unit vector that's in the same direction of v is going to be equal to our vector v divided by the length of vector v. This is our normalizing equation, if you will. It tells us how, given a vector, we can work out the unit vector, which is the vector in the same direction but with a length of 1. So again, the way this works out is that the unit vector v is equal to our vector, our original vector, divided by the length of the vector, which is going to be equal to, make sure I've got enough space to draw this in, it's going to be equal to the x component of the original vector divided by the length of the vector, and that's going to be our new x component, and then it's equal to the y component of the original vector divided by the length of that vector as our y component. So what we're doing when we normalize a vector, and we can normalize any vector, it doesn't matter how many components it has, we basically work out the length of the vector and we divide each component of the original vector by the length of the vector to generate the corresponding component in the unit vector. So x gets divided by the length to generate the x of our unit vector, y gets divided by the length to generate the y of our unit vector. But let's see, does this actually work? Does this actually give us a length of 1? Well, to do that, we really need to use some examples. We need to plug some numbers into our equation. So I'm going to bring up a new whiteboard in order to do that. And I'm going to say we have some vector. I'm just going to say we have a vector A, and I'm going to randomly choose some values for this vector. So I think we're going to have 6 in x and maybe 5 in y. So first thing I'd like to do is I'd like to show you, although it should be pretty obvious because we're traveling 6 units in x and 5 units in y, that this doesn't have a length of 1, a magnitude of 1. But I'd like to calculate the magnitude of this vector, A, to show that it's not the length of a unit vector, and also we're going to need to know the length of this vector for our later calculations. So we know how to calculate the magnitude of a vector. the magnitude of a vector in a 2D Cartesian vector is equal to the square root of x squared plus y squared, which is equal to the square root of 6 squared plus 5 squared, which is equal to the square root of 36 plus 25, which is equal to the square root of 61. Now that's not going to be a nice round number, but I am going to use a calculator to work this out. So we have 61. I'm going to take the square root of 61, and that gives us 7.81 roughly. So I'm going to write approximately equal to 7.81. 7.81. So that's the length of A. We can see A is not a unit vector, and hopefully that was quite obvious just from the components we're dealing with, because if we are traveling 6 units in one direction and 5 units in another direction, that vector obviously is going to be longer than 1. We know that from Pythagoras' theorem, but for those of you who weren't 100% sure of it, we can work through using our magnitude of a vector, which of course was derived from Pythagoras' theorem, and find the length of that vector is 7.81. So that's the length of our vector A. But what if I wanted a unit vector A hat? So what I want to do is I want to normalize A so that A is now a length of 1 but containing the same direction. So it's the same direction as before. So we saw that before we're sort of traveling kind of like this, I guess. Now I want a vector that has the same direction, but I want it to have a length of 1. So if this is A, this is going to be A hat. The same direction of vector, but it has a length of 1. Now we saw how to do that. We saw that the normalized version of a vector, a unit vector, is equal to the original vector divided by the length of the original vector. So we know that the length of our original vector is approximately 7.81. So this is approximately equal to A divided by 7.81, which we know that means we need to take each component of the original vector A and divide the x component by that 7.81 to get the new x component, and we need to divide the y component by 7.81 to get the new y component. So this is approximately equal to, I want to make sure I've got enough room to write this, so our x component was originally 6, so it's now going to be 6 over 7.81, and the new y component is 5 over 7.81. So again, we originally had an x component of 6. We've divided that by the length of the vector to generate the new x component of our unit vector. We had a y component of 5. We've divided that by the length of our original vector to get the new y component of our unit vector. So this is our unit vector approximately. And again, I'm going to use a calculator to work these out to rough values. Now, each time we're approximating values here, so for example, when we approximated the square root of 61, now if I approximate these divisions, we're obviously going to have some rounding errors, and that means if I was to work out the true length of this vector, it's not going to be exactly equal to 1 because of our rounding errors, but it should be close enough, and then I can jump back and actually show the mathematically rigorous way of writing this and then working out the length, and we can see that indeed it does have a length that is exactly equal to 1. But I wanted to show this with numbers first, so that those of you who aren't necessarily so familiar with some of the techniques I'd need to use for the mathematically rigorous working through, I wanted those people to at least be able to follow along with numbers, because hopefully you're all very comfortable dividing numbers, working out the square roots of numbers on a calculator and the like. So hopefully everyone can follow this, and those who maybe get lost in a second when I go through a more mathematically rigorous version, at least they've seen that it does pretty much equal 1 because of our rounding errors, whereas otherwise you might get lost. So I did want to point that out, that we're not going to have a length exactly equal to 1 because of our rounding errors here. So continuing on, we know this is then approximately equal to, so if I bring up another calculator, so I need 6 divided by 7.81, so 6 divided by 7.81 is going to give me 0.768. Yeah, we'll use 3 decimal places, so 0.768 in x, and we can then work out y, so 5 divided by 7.81, And this is going to be 0.640. So 0.640. Fantastic. So this is our unit vector. A hat has an x component of 0.768 and a y component of 0.640. So what do we know about this vector? Well, we know because all we've done is scaled the components by a value, and they've scaled by the same value, we've uniformly scaled our vector. That means we can guarantee that our new vector A hat has the same direction as A. But we don't yet know whether A hat has a length of 1. We think it should have a length of 1 because of the way we logically derived the fact that we divide by the original length, but we need to actually test this fact because we don't know yet that this gives us a length of 1. So how do we test this? We're going to need to find the magnitude of our unit vector, which is equal to the square root of, in this case, 0.768 squared plus 0.640 squared. So that's going to be equal to the square root of, I'm going to bring up a calculator, so we want 0.768 squared plus 0.640 squared, which is going to be equal to the square root of almost approximately 1. So we can see we're not going to get quite the right answer. So it's about 0.999, which is equal to, and again, this is because of our rounding errors. If I bring that calculator back and find the square root, you can see the square root of that is about 0.999. Which, if we rounded this, of course, would be equal to 1. Now, why didn't we get 1 exactly? Again, it all comes back round to the fact that we have approximated values. We approximated that square root of 61. So already we've lost some of the accuracy because of that approximation. Then when we divided by 7.81, so when we divided by 7.81, that again has we've used that non-accurate number, and then we even rounded the results of those divisions. So because of that, our result is not exactly equal to 1, but it's close enough to 1 that we can see, hopefully, using numbers, that this does work. This method does normalize our unit vector. Now, I said a second ago I want to show a mathematically rigorous way of proving this, if you will, but that there was a few steps involved that might lose a few of you that maybe didn't have the required background knowledge for following along those steps. What those steps are going to involve is, instead of evaluating the root of 61 as being approximately 7.81, what they're going to do is, I'm going to take the root of 61 and leave it written as the root of 61. So I'm going to need to bring up a new whiteboard, I guess, or maybe I can work next to this. We'll have to see. Now, I think I'll bring up a new whiteboard just to make sure everything's as clear as possible. So if we recall, our original vector A is 6 in x and 5 in y. So 6 in x, 5 in y. And we calculated that the magnitude of A is equal to the square root of 61. Again, we calculated that a second ago. We saw the magnitude of A is equal to the square root of 61. And I appear to have erased everything, so allow me to write this again. So A was 6 in x, 5 in y, and the length of A was equal to the square root of 61. Fantastic. So what I'd like to do is I'd like to normalize A, but I'm going to keep the length of A written in this square root form. So I'm going to normalize A, so I'm finding A hat, the unit vector that was in the same direction as A. We know that's equal to A divided by the length of A, which is equal to A divided by the square root of 61. Which we know that means we have a vector that has the original components of A each divided by the square root of 61. So the x component of A was 6. So 6 divided by the square root of 61. And the y component was 5. So 5 divided by the square root of 61. So this is our unit vector. This is the accurate way of writing our unit vector. We have 6 over the root of 61 as our x component and 5 over the root of 61 as our y component. But how do we check that this is indeed a unit vector? We know again that the fact that we're scaling by the same value all of our components, we do have a vector in the same direction. This isn't a negative value, so because of that we haven't inversed the direction. We aren't traveling in the opposite direction. We do have some scaled version of A, but how do we know the length of that scaled version of A is 1? Well, to do that we need to find the length of this vector. So we're going to find the length of A hat, which is equal to the square root of our x component squared. So that's going to be 6 over the square root of 61 squared plus our y component squared. So plus 5 over the square root of 61 squared. Now this is a step that hopefully most of you will be familiar with, but if you're not familiar with it, I didn't want to lose anyone when we're trying to show how this works to give us a unit vector. So that's why I worked through with numbers first. And the step is that if we have a fraction squared, it's equal to the same as the numerator of the fraction squared over the denominator of the fraction squared. So it's equal to the square root of 6 squared over the square root of 61 squared plus 5 squared over the square root of 61 squared. So this is equal to the square root of 36 over, well, the square root of 61 then squared. They're going to cancel, so it's going to give us 61 plus 25 over 61. Now because these are the same denominator, we can combine them. So 36 plus 25 equals 61. So that means we have the square root of 61 divided by 61. We know, of course, that's going to give us the square root of 1. 61 divided by 61 is 1. And the square root of 1 is a value of 1. So when we work through this in a sort of more mathematically accurate form by keeping this written as a square root and then work that through, which obviously then cancels out that square root, we don't lose any accuracy in doing that, you can see we get a value of exactly 1. So to recap that, that means that if we have a vector, any vector, so if we have a vector v, to calculate the unit vector in the same direction of v, to normalize v, we say that v hat is equal to the original vector divided by the length of that original vector. And hopefully you've now seen not only the equation for doing this, but how that relates in terms of actually working it out. So we take each of the components and we divide each component by that original length. So now that we've looked at some examples of doing this and we've looked at the theory behind it, there's not a huge amount to it. It's not particularly involved. But I do want to set just a couple of questions to make sure you are fully understanding what's going on here. And so hopefully that will, if you do get stuck at any point, that will bring up where you're getting stuck and you'll be able to look back into the video and see perhaps which little bits didn't you fully understand. If you have any problems at all, you may be absolutely fine with this. So to do that, I'm going to set a couple of questions. The first question I'm going to set, as I scroll on back up, fantastic, is question 1. And I'm going to give you a vector. This is going to be a vector c, and this vector is going to be equal to the vector 8, 6. So our x component is 8 and our y component is 6. And what I'd like you to do, I'd like you to calculate what the components are of the vector c hat, please. So go ahead and give this an attempt. Once you have a solution, or if you get stuck, unpause the video and I will work through the answer here on the whiteboard. Okay, welcome back everyone. So we're trying to find the unit vector that's in the same direction as our vector c. So we know to do that, that c hat is equal to c divided by the length of c. So we first need to calculate the length of c. So the length of c is equal to the square root of our x component squared plus our y component squared. So it's going to be the square root of 8 squared plus 6 squared. That's equal to the square root of 64 plus 36. which is equal to the square root of 100. Now I chose numbers that would mean you'd get a square root of a nice square number, which means we can work this out as being a nice accurate number of 10. So there was no worries with losing any accuracy there. So we've got 10 as our length. So we know to work out c hat, we take our original vector and we divide it by that length. So c hat is equal to our vector c divided by 10. And we saw what that means is we take our vector and we divide each component of our vector by 10 in this case, because we're dividing by 10. So that's going to be equal to a vector. And the x component of that vector is going to be the x component of our original vector, 8, divided by 10. So 8 divided by 10. And the y component is going to be the y component of our original vector divided by 10. So 6 divided by 10. Well, because we're dividing by 10, we can actually easily write this as a nice round decimal value. So this is going to give us the vector, so c hat, our unit vector, is equal to 0.8 in x and 0.6 in y. So this is the answer I was looking for. But just to prove to you that our method does work, it does give us a unit vector, I'm going to do a little bit extra now. I'm actually going to find the length of our unit vector and prove to you that that length is a value of 1. So we're going to find the length of our unit vector. So that's equal to the square root of 0.8 squared plus 0.6 squared. That's going to be equal to the square root of 0.8 squared is going to give us 0.64, plus 0.6 squared is going to give us 0.36. Hopefully we can immediately see that's going to add to a value of 1, which we know the square root of 1 is a nice whole number, 1. So we do have a perfect unit vector there. It has a length of 1. But again, that wasn't what I was asking in the question. I was simply asking for the components of that vector. So as long as you said that c hat is equal to 0.8 in x and 0.6 in y, that was what I was looking for. If you got stuck at any point, first thing you want to make sure, of course, is that you remembered this equation correctly. You got this equation correctly. To find a unit vector, we take the original vector and we divide it by the length of that vector. As long as you remembered that, then make sure that you worked out the length of the vector correctly. Make sure you did take the square root of x squared plus y squared. And then just make sure there weren't any numerical errors as you worked through that. And hopefully you did get 10 as the length. If you got that correct, then just make sure that you were using this equation correctly. So you take the original vector, you divide it by 10. That means to take each component of the original vector and divide each component by 10. And that should have then given you, either you had it written in fraction form, maybe 8/10 or 4/5, or you had it written in decimal form. But as long as the value is correct, then that's the answer I was looking for. So that's question 1. I'm going to set one last question here. So I'm going to bring up a new whiteboard for that. Now, once you've worked out this question, you're going to see it's a little bit of a trick question, but it allows me to sort of introduce a little bit extra theory, though it's pretty obvious theory. But I'm going to say we have a vector d, and that vector is equal to 4 in x and 3 in y. And I'd like you to work out, and that's terrible drawing there, I'd like you to work out the unit vector of d. So I'd like you to work out d hat. Now again, this is a little bit of a trick question. Hopefully that will become apparent once you've got the answer, but it does allow me to bring up one little bit more piece of theory before I conclude this video. So go ahead and give this an attempt on your own, and when we come back, I'm going to work through the solution here on the whiteboard. Okay, welcome back everyone. So hopefully by now we're quite comfortable that to work out a unit vector, we take the original vector and we divide it by the length of that original vector. So the first thing we need to do is work out the length of d. So the length of d, the magnitude of d, is equal to the square root of the x component squared, so 4 squared, plus the y component squared, so plus 3 squared. Now again, I chose these numbers to give us nice round numbers. So 4 squared is going to be 16, plus 3 squared is 9, that's equal to the square root of 25, which is equal to 5. So I chose these numbers specifically to give us a nice round whole number when we take the square root of it. So we've got the length of D is equal to 5, so we now need to divide D by 5. So D hat is equal to D divided by 5, which is equal to, if you recall, we take each component of the original vector and we divide each component by 5. So our x component is 4. So we need to take 4 divided by 5 to give us the new x component. Our y component is 3. So we need to take 3 divided by 5 as our new y component. Now if we were to write this in decimal form, we'll see that 4/5 is 0.8 and 3/5 is 0.6. So why is this a trick question in a way? Look at the vector we have here as our d hat, and then think back to question 1. So 0.8, 0.6, 0.8, 0.6. They are the same unit vector. But why is that? Well, that's because if we look at our vector, we had vector d is equal to 4, 3, and we had vector c in the previous question was equal to 8, 6. Notice they are two different vectors, they have two different lengths, but the direction of the vector is the same. One is a scaled version of the other. We could write, as I scroll down, I'm going to rewrite D, rewrite C, and then talk about this a bit more. So D was equal to 4, 3. C is equal to 8, 6. We could write that C is equal to 2 times D. We can hopefully see that C is equal to 2 times our vector D, which was 4, 3, because that gives us 2 times 4, which is 8, and 2 times 3, which is 6. So we can see that C is twice D, and because we've scaled D by a scalar value, and that scalar value is positive, we know they have the same direction, just one of them is twice as long. So C is twice as long as D. Now, when we normalize these vectors, we're obviously disregarding the length. We're making them so that both of them have a length of 1. Well, they share the same direction. That means they're going to have the exact same unit vector, because when we normalize them, we're going to scale both of them down so that they have a length of 1. If we scale D down to have a length of 1 and C down to have a length of 1, we're going to get the exact same vector. So it's kind of a trick question and kind of not. I just wanted, firstly, for you guys to be practicing working out how to normalize a vector. But if you noticed that we had the same unit vector, it's because they have the same direction. If they have the same direction, they're going to have the same unit vector. Because again, though this isn't really a mathematical definition, the mathematical definition is it has a length of 1. I like to think of it as being it only encodes direction. Because the length is equal to 1, and 1 really doesn't have that much effect on anything, it means that we are only encoding direction. Therefore, if we have two vectors with the same direction, and we convert them, we normalize them into unit vectors, we're going to get the same unit vector. And with that, that is going to wrap up everything that I wanted to cover in this video, and thank you guys for watching.